Hi everyone, so today's lesson we'll be looking at non-polar molecules, and can you remember what we did last time? So we were looking at electronegativity and polar bonds. So we're going to use that to figure out if whole molecules are going to be polar or not polar. So when we do this, we need to determine its shape and whether it's got polar bonds. So we need to look at the electronegativity. We use electronegativity to decide whether the bond is polar, so covalent bonds, that means where the electron pairs are shared between two atoms. So if it's got an electronegative atom, that means it's got one that pulls the electron density closer to it, it's going to have a polar bond. And then we can also use the VS-EPR theory to look at whether the molecule is going to be symmetrical or not symmetrical in shape. So we use this to predict the shape of the molecule and to see whether the polar bonds can either add together or cancel out. So if one molecule contains more than one or more polar bonds, then we can see if it's got the whole molecule is going to be polar or not. If the polarity of the bond is present, so like in the water molecule, we have the O pulling the electrons closer than towards the H, so it goes this way. There's going to be electrons around here and more positive charge around here. So on this bond, we're going to have a polar bond. So the negative side here and the positive side here. And then the same goes with this side. So when this happens, we know we have a dipole, and then we can then add together the vectors, so the direction and the size of the charge together to see if the molecule is going to be polar or not. So in this case, we have the negative electrons going towards the oxygen, so negative that way. The arrows point towards the negative charges, so this way and this way. When we add them together, we're going to get an overall charge over the whole molecule in this direction. So heaps of negative charge around here, more positive around here. So when we have the dipoles represented by the arrows, we have the negative end at the arrowhead. So the arrow is pointing in the direction of the negative charge. So from the known molecular shapes of the molecules that we looked at before, we can then add together the direction of the charges. So with the arrows, we add them together, and then this gives us the overall dipole on the molecule, which is represented by this arrow here. So to determine if the molecule is going to be polar or not, we need to look at two things. The first is whether there's going to be any polar bonds or not. So that's when we look at the electronegativity of the bonds, of the atoms, and then decide whether the bond is going to be a dipole or not. So that's the first one. Number two, we're going to look at whether the molecule, the shape of it, is symmetrical or not. So if it's symmetrical, then it's going to be a non-polar. If it's not symmetrical, then it can be polar. So for example, we have beryllium difluoride, which is represented here. Beryllium in the middle with two fluoride atoms on the side. And in this case, the molecule is going to be linear because it's only two other atoms around the central atom. So if it's linear, it's symmetrical along this plane. So along here. So the fluorine atoms and the beryllium atom are bound together in a covalent bond, and because fluorine is a very electronegative atom, we know this from the table before, it's going to pull the electron closer to it. So there's going to be a slight negative charge over each fluorine atom compared to the beryllium atom. So each of the bonds are going to be polar. So there's two polar bonds represented by the arrows here. So the electrons are going to be pulled here, and then there's going to have a slight negative charge on this side. Arrowheads going to the negative end. Because there's two dipoles, but they're in the same magnitude but different directions, so opposite directions, they're going to cancel out. So when we add the two arrows together, the vector sum is going to add to 0, and therefore the whole molecule is not polar because they're pulling in opposite directions at the same amount. So another example is going to be boron trifluoride. So boron trifluoride is got 4 atoms in it. The boron in the middle with the 3 fluorine atoms on the outside. Because we know that fluorine again is electronegative, it's going to pull the electrons closer to it and have a slight negative charge over the fluorine atom. And then the boron is going to be slightly positive compared to the fluorine. So there's 3 polar bonds because there's 3 fluoride atoms bound to the boron. And the molecule is going to be a triangular planar shape. So it's going to be flat with the in a shape of a triangle like that. So because we have 3 dipoles pulling in different directions, but all in this, they all cancel out because they're all 120 degrees apart. They're pulling in the same amount and in opposite directions. We're going to add them together and it'll give us 0. So the whole molecule is going to be nonpolar. It's nonpolar. So in summary, we need to look at the electronegativities to decide whether bonds are polar or not in the molecule. Then we need to add them together to see if it's going to have a net dipole or not. In our examples today, they're not polar because the whole molecule is symmetrical, and therefore they're all pulling in the same opposite directions in the same amount, so it's going to cancel everything out and be a nonpolar molecule. So now that we all know this, we can look at the questions to test if you understand. So question 1, compare the shape of the molecules of water, ammonia and hydrogen sulfide. So we need to look at 3 things. If you can remember before, ammonia, do you remember what shape it is? And then what about water and hydrogen sulfide? So we'll look at ammonia first. Ammonia, remember, has 1 nitrogen atom surrounded by 3 hydrogen atoms. And remember, how many lone pairs does it have? It's got 1 set of lone pairs. So if there's 1 set of lone pairs plus 3 hydrogens, it's going to have 4 constituents around it. So we're going to have a tetrahedral type shape, but because the lone pairs take up one of the spots on the tetrahedron, it's going to look like a pyramid, and that's why we get a pyramidal shape. So water and hydrogen sulfide, how many lone pairs do they have? They both have 2 sets of lone pairs, so the lone pairs are going to sit around here. And because there's 2 sets of lone pairs, it's going to push the bonds to the hydrogen down, making it into a V shape or a bent shape, which is why both of these, because they have 2 sets of lone pairs, give us a bent shape compared to the pyramid shape of the other one. So next, question 2. Use diagrams to help explain the molecular structure of the ammonia molecule and to determine its shape. So we need to make sure we draw diagrams instead of just writing in words. So electron pairs are arranged in the shape of a tetrahedron. 3 of the corners we said are for hydrogen, and then 1 of them is going to be the lone pair. So this is going to push the other ones, the hydrogens down, making it look like a pyramid shape. So if you remember our Lewis dot structure from our first couple of lessons, we know that nitrogen has a set of lone pairs represented by 2 dots, and then 3 hydrogens bound to it, and with the covalent bonds being lines. So we know that, and then because we know that the electron clouds are going to repel each other, they're going to form a tetrahedral shape like this, with 1 lone pair taking 1 of the corners, and then the 3 hydrogens on the others. So when we look at it, we can't really see the lone pairs. So the nitrogen will be at the top, and then the 3 hydrogen atoms coming down to make the bottom of the pyramid. So next, question 3, how is it possible for a non-polar molecule to have polar bonds? So we need to distinguish between polar bonds and then the overall shape of the molecule, whether it's polar or not. So a polar bond is a covalent bond, a shared pair of electrons, remember? Where 1 atom is going to be electronegative, and that means it's going to pull the electrons closer to it. So the electrons are going to be closer to the highly electronegative one. So one end of the bond is going to be slightly negative, and one end is going to be slightly positive. So a non-polar molecule is one where all the polarities of the different bonds are going to cancel out. So there must be symmetry. If there's no symmetry, we can't get them to cancel out because it's not symmetrical. So that means when we add all the vectors together, so all the direction and the sizes of the dipoles, we're going to get a net of 0. So that means it's going to be non-polar. So question 4, indicate the polarity of the Cl oxygen bond with the polar arrow. So do you remember how the arrows point? So we need to make sure that the arrows point towards the negative side So in ClO, is one of them going to be an electronegative molecule, atom? Yes, because we know oxygen, fluorine and nitrogen are one of the most electronegative ones. So oxygen is going to pull the electrons closer towards it, and that means it's going to be slightly more negative compared to the chlorine. And because we know the arrows point towards the negative, we need to draw the arrow towards the oxygen, just like that. Finally, question 5. Explain why beryllium difluoride is a nonpolar molecule. So we looked at this just then in one of our examples, and we know that beryllium difluoride is going to have the beryllium atom with the 2 fluorine atoms on each side. So this means it's going to be a linear one because there's no lone pairs to push it in any other direction. So it's linear like this, with the fluorine atom being more electronegative, pulling the electrons closer to it and making it more negative on this side, and the same on this side. So this here in the middle is going to be slightly positive. So we have 2 sets of dipoles here on each bond, one this way and one the other way. But they're both the same size because it's the same set of molecules. It looks exactly the same. So because they're the same but in opposite directions, what do we know? That means it's going to be symmetrical along here. So this side and this side are going to be the same. And therefore when we add the vectors together, they're going to have a net sum of 0. So that means the whole molecule is nonpolar. So just remember, when we go through nonpolar molecules with polar bonds, they need to have symmetry. So just to recap, what we did is we looked at the shape of the molecule, decide if it's symmetrical or not, and then we also need to look at the bonds, whether they have a dipole on one side. So is one electronegative or not, and if it is, that means it must be a polar bond. And then we decide whether they cancel each other out, and if they do, that means it's going to be a non-polar molecule. So next lesson we'll look at polar molecules.